let G connected linear algebraic group. And X is just normal algebraic variety on which our algebraic group acts.
So probably we should fix the ground field.
Okay, let K is algebraically closed. I guess it denoted as this, and has K has characteristic 0. Then there is a statement. For all points from our algebraic variety, there exists an open G-stable quasi-projective open neighborhood of X. Yeah, and that is, you can always cover your normal algebraic variety by open G-stable quasi-projective subsets. It was the first statement, and second, I decided to denote it this. And the second, if your algebraic group G is a torus, then for all points from X, there exists open G-stable and affine neighborhood of X. Okay, and you understand that this doesn't mean that this U in this case is affine. This U is just another
You said that
substance.
U can be chosen to be affine.
Yeah, yeah. There exists. Okay. Okay. What about the plan of my speech? At first, I go through the proving this theorem. I will prove both of these statements. I prove this. there will be some lemmas which I think I just formulate first of all, and if I have time I will prove them in the end. Okay, and next I prove point B, and finally we will say some words about contradictions to this statement when G is not a connected group. Okay.
You mean counterexample?
Yeah, counterexample. Okay, fix an arbitrary point from X, and of course there exists at least an affine open subset in X which contains our point X. It's just virtue of definition of abstract algebraic variety. So yeah, but this U, of course, is not necessarily G-stable. But we will see later that this guy is what we need. Okay, so we need to prove that this subset is G-stable.
So this subset is G-stable automatically. Probably we should.
Oh, sorry, quasi-projective, of course. Okay.
And also this opens automatically.
Mm-hmm. Should be to that U prime. Okay.
So this will be U, I guess.
Yeah. This denoted as U. Yeah, from the formulation. Okay, now consider the complement of U in X. Dx minus U prime. And lemma 1. This thing, the complement of U prime, can be, of course, can be decomposed into irreducible components. But actually, all of these components are prime divisors.
And this is the main point.
Mm.
So the main point is that all the components have dimension. Codimension.
Yeah. Okay, the part of the audience have already seen this statement about 2 weeks ago, and actually it is not very hard, I think. So
We're going to skip the proof.
yeah.
Isn't it only me and Veronica who have the proof? So it's supposed to...
Kirill,
No, Kirill is.
you can prove it by contradiction if there exists at least one component with codimension equal or greater than 2, then okay, if you want, I can prove it in the end. Okay. And lemma 2. What we will use for all I from 1 to s, these prime divisors are Cartier on this subset. On x minus intersection так. Okay. This statement is you can prove this lemma in some. Okay, I just understand that I haven't got enough time to this, so let me move on to the proof of A itself. Okay. Consider a divisor delta, which is the sum of these prime divisors. And of course, this divisor is Cartier on this. Sorry. This divisor is Cartier on this complement. Okay, just. Wait, yeah, thank you.
This is U actually, yes, this is actually U just.
Sorry?
Well, this x minus this intersection is just U.
Yeah, you can see that it is the same as U. Okay? And we will work this with this divisor. Okay. Now consider the coordinate ring of U prime. And let it be generated by regular function 1, etc. Fn, where, of course, all of this function is regular on our U prime. And since that the divisor of any function f sub I is just a linear combination of these divisors. It is true. It is true just because f sub I regular on U prime.
Always divisor, but divisor of poles, yes.
Yeah. Oh, yeah. These functions have no poles in U, so the divisor of poles is has this type. Okay. Now put M is the maximum of all coefficients k sub Eg, and then you can construct a canonical section first of all, you can construct a line bundle and canonical section which divisor is delta. It is statement.
You want to take delta or m delta?
M delta. I just wanted to say delta and m delta too. Okay, there exists section which I decided to denote as
So
this.
it would be better to introduce the line bundle at the beginning.
I want to do this. Okay.
So O of m delta is that very line bundle
Yeah.
associated with.
The thing is that m delta is a Cartier divisor, so m And we know that each of Cartier divisor corresponds to a line bundle and this section, which divisor is M delta. Okay. Now.
Maybe it's worth to recall.
Sorry?
Maybe it's worth to recall how we construct this line bundle and section.
Okay. What I can to remove? Sorry. Okay, why this line bundle and the section exist? We know that D is Cartier divisor. Next. By definition, it means that you can cover your X by some open subset such that D would be a principal divisor on every U sub I. Means D intersect with UI. Okay?
So I think on the left hand side you should also stick to U.
Oh, yeah. Thank you. And to define a line bundle is the same as to cover your X by open subsets.
I guess this is not this list, so there are more conditions. So at least that the quotients Fi by Fj is invertible on each intersection. So this is part of the construction.
Maybe we need only
Yes, we need only this.
from the left to the right.
I guess that we just use this construction, and so we don't use all the conditions.
So we can anything this to one direction.
Oh, yeah.
Yeah, we just need from this to that.
Yes.
Okay.
if you don't put all the conditions, that you should erase
Mhm.
them on the top.
Okay, yes, okay.
Mhm.
Okay, maybe it's fine.
Okay.
So this should be read as, so it follows from the definition of a Cartier divisor that X can be covered by such open subsets, and there is a collection of operational functions.
The quotient of functions, it's corollary of this. So if we take the quotient of functions, yes, the divisor of this quotient will be zero intersection. So it's a function.
Okay, maybe. Okay.
We can
So we should check.
come back.
Okay. So we just need to make some respective gluing functions on intersections.
Well, at least of normal vertices.
Yeah, you're right. So we now construct a line bundle.
For
So these are transition maps.
yeah. Yeah. We need to construct these functions such that first of all G is from vertibles. Okay, so if we make these functions,
Last line, the second one,
yeah, then
J.
G, K, and Ki. Okay, then we will get a line bundle. So how to construct these functions? In our case, we can just define G sub Ig as Fg divided by Fi. Okay? You see that all of this properties is true, and And what about section? We need also a section. Define section as section S as follows: S on UI is equal to Fi. But of course you need to check what happens in intersections.
You mean that on this UI our line bundle is trivial, yes, and the section is the same as regular function.
Yeah. And if you take any point from intersection u sub I, u sub g, then what happens? X go over S to this pair, X Fi X, and if you act by this function g sub ig, then you will get this pair X FGX. Okay, but this pair you also will get if use just S. Okay, because X is from UI and UG. So, is it clear? Okay, now return to our statement. S0 is Cartier. We get line bundle and respective section. Okay. Now, by linearization, we can lift our action G from X to our line bundle. So yeah, the action on X lifts to the action on our line bundle. Okay. Just by G linearization, or if this action is not G linearizable, then we can there exists another connected algebraic group G prime, such that which linearizable, and this is a statement. You of course can find it in reference for authors.
But
this was discussed before in September.
Yeah, yeah. Or
So we choose M such that this
uh,
projection will
about I didn't
No, we can
say
replace
some.
G by a covering group
Yeah.
in such a way that this line 1 will be zero.
Okay, and besides that, the G prime. Okay, and besides that, there exists G stable or G prime stable, G stable finite dimensional subspace M in our space of global sections. I'm doubt. But
Which contains S0, right?
yeah, which contains S0. Moreover, we can define another sections S sub G, which are Fg multiplied by S0. And you can see that these sections S sub G also contains in this space. Okay, just because the divisor of this G is divisor Fg plus divisor S0. But we know that divisor 0 is M delta. So if you enter divisor of Fg, divisor of poles, of course. It is M delta. It is from this.
No.
It's better to erase infinity.
Sorry?
It's better to erase these infinity signs
Why?
because we consider just the divisor, the whole divisor. So you just want to say that this divisor is effective, right?
One moment.
So the point was to eliminate for that divisor of points.
Yeah.
This equation is not true. Divisor of poles of product of well. Two.
Because the divisor
Yeah.
of
It does,
zero
yeah.
is just zero.
Understand?
Doesn't make sense.
Okay, thank you. Okay, therefore, S sub J contains.
So you can add here that it is greater than or equal to zero, so it is effective.
Okay. And now.
So as a consequence, this SJ is a regular section.
Yeah.
It is
Yeah.
a global section.
So now we can. There exists G-stable finite dimensional subspace, which contains not just S0, but also these sections. Then Okay. Mhm. Mhm. Okay. And this M one moment. And this M evokes to this rational map. From U which is G U prime to the projectivization of dual space of M. In the coordinates, it is this x okay. Is it clear? You can consider why this in that. You can consider this.
We claim that M has dimension n plus 1.
Yeah, I want to say that.
No,
I just hope to this.
yes, some sections. Well, you need to add some other sections.
Some other coordinates.
Mm-hmm.
So this is coordinates.
One moment, I think about next steps. Okay. Mm-hmm. Is it clear now?
In this form, okay.
Mm-hmm. And actually, this map is defined in a whole U. And this map is an embedding Y. You can at first consider phi on U prime. Sorry. We know that U prime is our open subset in U, on which S0 S0 is not 0 on U prime. Well, just because the divisor of S0 is the complement of U prime in U. So you can say that U goes to this affine chart. Where okay, and it is the same as 1 1. Okay, just because
On U or on U prime? Where we can divide by S.
on U prime, thank you. Okay, and now you see that phi is defined on whole U. Sorry. And moreover, it is an embedding.
So I still sure that we should take M. Probably we could take the linear span of these sections. Then it will be okay.
Why not is it just say?
So as I understand, we don't need it to be just tables in order to work for this construction.
Oh, no, I think we will want to this might be G2N. Well, actually, to prove that we'll obtain quasi-projective parity, yes, we don't have the whole time.
Okay. And why is it embedding? Because this map corresponds to the dual homomorphism between two coordinate rings. And you see that this map is surjective because you can get every generator of U prime of this ring. By this way. And this generates this ring. So this map is surjective, and therefore this map is closed embedding. Okay, it was about U prime. What about U? Why this phi is an embedding? Так, где бы? Наверное, там. We can just act to this map by any element of our algebraic group G. So for any G from G, G U prime embeds to this chart. G at 0 is not equal to 0. And these subsets cover our open subset U. Can remind you. Okay, so our map phi is defined in whole U, but it is also embedded. This is also closed. And why phi is an embedding? Because you can consider the picture. Okay, this is G1 U prime and this G2 U prime. And we know that these subsets go embed to these charts. But what happened with points? One moment. From. We need to prove that phi is an embedding. So what if some points from this and this, for example, go to the image conside. This can be a problem. Is the image of two points from different subsets are the one point. But but it is not. It can't happen because one moment.
Well, we know that the complement to U prime is divisor of S0, yes?
Yeah.
So the complement to G1 U prime is divisor G1
Yeah, yeah.
S0.
Thank you. In this complement of G1 U prime, G1 S0 is equal to 0. Yeah. So points from
The bottom point can the initial
yeah. Points from this complement have to go to this subset, and points from this to this. And of course, on this intersection, our phi is an embedding. Okay, so phi is an embedding on our open subset U. Okay, so we get that we always can embed U to projective space and embed. This map is not necessarily closed because this the union of these charts is maybe not the whole projective space. So U is just a quasi-projective.
It will be closed in the union of the chart, yes?
Yeah. Okay, so I think we proved the Sumihiro theorem. U is open, U is G-stable, U contains our fixed point X, and U embeds to a projective space. Okay. Let's move on to the proof of point B about torus group. I can remind you this statement. T acts on a normal algebraic variety, and then you can cover your X by open G-stable affine subsets.
Это та причина, по которой веер не выбрались из концов. that it's true.
Why in Russian?
It is the reason why the fan of toric varieties consists of chorus.
Proof. Actually, Sumihiro denoted this statement as a corollary from previous statement. But previous statement he also denoted as lemma 8. Okay. Proof. By virtue of Sumihiro theorem, we can assume that our normal variety X is quasi-projective, on which torus T acts linearly. Okay? Okay, and there are two cases. Let me find them.
Yes, we'll do it.
So we assume commutative with the space
Yeah.
which takes linearly.
Maybe write down that X is contained in some projective space.
Okay, X, for example, contains in M with star. Okay.
That acts on B.
Mm-hmm. Yeah. And there are two cases. First case, it is when the closure of X coincide with X. Mm-hmm. Then,
So X is closed.
yeah, X is closed. Mm-hmm. Then B is true because you can represent your projective space as the union of of an affine charts. Where for every I from 0 to n every affine chart is T-stable. Okay? Well, you can just choose T semi-invariant homogeneous coordinate on your projective space, so it is true. And if you intersect your
So this means that inside V, we choose a basis which consists of
yeah,
single vectors.
yeah. Yeah, thank you. And if you intersect any of your affine chart with X, you will get an affine variety. Because
it is closed.
yeah, because it's closed. And this thing is T-stable too, because by our assumption X is quasi-projective T-stable, of course, by virtue of Sumihiro theorem. And our affine chart is T-stable too. Yeah, it is about this case when X is closed. Now, the second case when X is not closed. Then we can consider subset, the complement of our X in its closure, and this closed subset in this space, and put I is corresponding homogeneous ideal. Okay. Of course, this ideal is T-stable because by our assumption X is T-stable, so its closure, yeah, and the complement. And we want to find T-stable affine neighborhood for every point from X. So fix again arbitrary point from X, and let M to be its homogeneous ideal. Okay, and then you can see.
So we consider ideals in K of V.
Sorry?
Ideal where? So it should be in some range. When I
Yeah.
say that the ring is K of V,
Yeah. Так.
No,
no,
it's
no,
a
K of V.
I would want to say that it's how would you call it? homogeneous coordinate ring on the projective space, yes. But it's the same as K.
K, just.
Like KFV and
Mhm. Okay, thank you. Then you can see that.
Sorry.
Mhm. And then you can see that the ideal I is not doesn't contain in M. Okay, just because X doesn't contain in Y.
I'm sorry, what does it mean that M is a homogeneous ideal of F1? The maximum
Yes, it's maximal, but it will be homogeneous.
It's maximal and homogeneous.
And therefore there exists a function in the complement in this subtraction I minus M. And now I want to consider some subspaces. Sorry. Okay. Okay. First subspace space is W2. Let it be V prime. V prime is just a space spanned by these guys. For all G from our torus.
We take any function f.
No. This.
Any function which belongs to this set. So
On zero
Which is-
matrices. Set of matrices, on zero.
not necessarily homogeneous.
No, it's not homogeneous, yes.
Sorry.
We may take it.
F homogeneous, yes.
Homogeneous.
Okay.
Function.
Yeah.
Then we take its linear span.
Mm-hmm. Next is intersection GM and finally this. And
Prime or V?
V prime, thank you. And obviously this space and this are T-stable
Yes.
and of finite dimension. Okay, and then we can.
So what is final? What is the final? finite dimensions.
V prime and W okay, and
Do you claim that W is non-zero or not?
yeah, I think about just yesterday, and I found out that it doesn't disturb the next argumentation. So
it doesn't matter. You mean
yeah, maybe W is 0. And then we can write our V prime as follows to the sum plus some subspace Z. Since we act by torus.
Z is the invariant, please.
Sorry?
Z is T
T
invariant.
stable.
Yeah.
T invariant.
W is T stable, so there exists a T stable subspace Z. Next, then you can choose any one moment, choose okay, choose and then consider the hypersurface defined by this homogeneous function as T stable, of course.
Divisor is homogeneous, invariant and Z is here.
I guess the prime is homogeneous, right?
V prime is
Sorry?
The prime is homogeneous, I guess.
V prime
J, what about J? Homogeneous?
finite dimensional.
Yeah, those are homogeneous ideas. So all its shifts are also homogeneous and
Yeah.
Okay, everything is homogeneous, and so F can be chosen to be homogeneous.
And finally, the fine neighborhood of our fixed point x, which we desire, is the next subset. Consider U is x, the complement of this hypersurface. Okay? It is T stable and affine, because by our assumption x is quasi-projective, and the complement to hypersurface in quasi-projective variety is an affine. And finally, we need to check that
Why use affine?
X is, by our assumption, is quasi-projective.
Yes.
And S is a hypersurface.
Yes.
And then the complement is affine. Is an affine.
It will be true if X if X is projective, but when X is quasi-projective, it's not.
Perhaps we know that S contains Y. No?
Yes, because S contains Y, yes.
Is it true?
S. Так. Where my Y?
What will happen if X contains Y? I don't understand.
So we can extend X to be, so we can add Y to X, and then it will be projected. But afterwards, if we remove S from the projected.
So F belongs to the intersection of this ideality, and yes. And what is it mean?
So I guess it should contain Y, otherwise
Yes.
this is just false.
We need to check that F belongs to I, yes?
F?
F capital.
F capital belongs to Y, belongs to I.
Yes.
Mm-hmm.
F small was and I.
And why if F capital contains in Y, in I everything good?
In this case, S will contain Y.
Mm-hmm.
No, I is a U of Y.
I is the ideal of Y. So perhaps this point is somehow missing. Okay?
Mm-hmm.
Well, no, I think it's clear. It's because V prime F small was in I, yes?
Yes.
And V prime also is subset of.
Yes. Yeah.
Mm-hmm.
Yeah. So that's obvious.
Yes.
Okay. And
Everything is going inside I.
Yes.
okay. And finally, you can see that our point X contains.
Probably you could add a parenthesis explaining that this is because F is contained in I, F belongs to I, and so as a consequence, Y is contained in S. Y is contained in S.
Okay. Is it clear why X?
Can you explain us? Because F is not in W, yes? W is
Yeah.
Yes.
Okay. Now we proved this corollary.
We have put X into an affine T-stable open subset.
Yeah.
Okay.
Okay. What's about time? About some words about counterexample.
Oh, yeah.
Mm,
Counterexample is a good idea.
Ivan Vladimirovich suggested these thoughts. Okay. He said that we just enough to prove. Okay. Can I do? What if G is disconnected?
We use that G is connected only when we we use
We linear.
Yes,
we
when we-
consider linearization.
And Ivan Vladimirovich suggests to consider the case when G is a finite group, and then it is enough to prove that not every affine that not every G orbit contains contains in one affine subset. Sorry.
So there is an example action of finite group such that there is an orbit which is not contained in a affine variable. Yes.
Yeah.
And if we have quasi-projective, yes. In quasi-projective, every finite set is contained in a finite
Yeah.
subset.
Exactly.
Yes.
Is it clear?
Yes.
I don't know.
Oh, I think yes.
And in the theory of invariance by Winberg-Popov, you can find the claim that for finite group, every G orbit contains in affine subset.
G is contained.
Sorry,
Is contained.
is contained in affine subset if and only if there exists a respective geometric factor quotient. Yeah. So they therefore we need to find X and G for which geometric quotient doesn't exist, and Nagata in the same book, Theory of Invariance, there is a reference to a work by Nagata in which required example constructed for G is 0, 2. But honestly, it was too hard paper by Nagata, and I didn't understand there something. But nonetheless, the condition of connectivity is important in Sumihiro theorem. Okay, that's all. Then.
Thank you. Are there any questions?
And the condition of normality is also important, yes?
Yeah, we.
Is this
If you see the proof of the theorem, we actually use the condition of normality in lemma 2. But
About Cartier dividers.
yeah, about Cartier divisors on the complement of intersection. Yeah.
When the group is not connected, do you call it disconnected or?
Sorry?
I have never seen that the group is called disconnected.
This is the same.
The same is not connected.
Yes.
And another variant non-connected. Yeah?
Is not connected.
Connected.
Not connected. Okay.
In two words.
But disconnected is a nice word.
Okay.